We are doing current electricity, and we have already done the concepts of voltage, that is a potential difference, current, and reached the resistance. So those who are watching this for the first time, please watch the other sections also. The links are given in the description box so that you get the continuity of the lesson. So last when we did resistance, we found that the resistance will depend upon length and area, isn't it? So when length is changing, the resistance will be changing. When area is changing, the resistance will be changing. So we found that. So resistance is actually okay with the change, or he is ready to change when length is changing. He is ready to change when the area is changing. Now today we are going to introduce another person, that is the resistivity. Let us see how is he. See, when the length is coming and asking whether he could change according to length and whether he could change according to area, the resistivity is stubborn. So he is saying that he won't change, and he got his own identity. So today we will learn about this concept of resistivity in detail. So today's topic is resistivity. It is represented using Greek letter rho, like that. Now we will go to the details. So in order to learn the resistivity, we need the relationship between the resistance, length, and area. So we found that the resistance of a conductor, R, is directly proportional to length. That means if length is increasing, the resistance also will increase. Then also we found that resistance is proportional to 1 upon area, or resistance is inversely proportional to area, which means if area is increasing, the resistance will be decreasing. And we found that when more area is there, more charge carriers can move easily through the conductor, or charge carriers will be can easily move through the conductor if area is more. So these are the two relations that we have seen in the last class. So from these two relations, that is a relation number 1 and relation number 2, if you are going to combine those two relations, you can write the relation as resistance is proportional to length upon area. That is combining 1 and 2. So this is a proportionality relation. It is not an equation. You know, when you have to convert the proportionality relation to an equation, we use a proportionality constant. So here we can say R is equal to, there will be a constant here, a constant multiplied with what? Length upon area. Okay, and this constant that we multiply, that proportionality constant, is actually the resistivity. So this constant is resistivity, and we represent resistivity using Greek letter rho, somewhat similar to writing of P, like this, rho. So we'll modify the equation as R resistance is equal to rho multiplied with length upon area. So this is the equation for resistance that relates length and area, where rho is the resistivity, L is the length and A is the area. Now if A is area of cross section is circular, then the area will be pi r squared, area of the circle. So the equation can if you want, you can rewrite it as R is equal to rho, the resistivity, multiplied with length divided by pi r squared, where r is the radius of the conductor which we are using. So that is the relationship between resistivity and R. Now resistance. Now let us define what is resistivity. I told that resistivity is not depending upon length and area and all. So let us see what actually is resistivity. I am going to rearrange this equation, and I am going to write it in terms of resistivity rho. So rho is equal to R multiplied with pi r squared. It is cross multiplication, simple cross multiplication, divided by length. Or if you are writing it in terms of area only, instead of pi r squared, you can write it as rho is equal to r multiplied with area divided by length. Now suppose area is unity, that is area, the value of area is 1 or unity, and length is also unity, that is 1. If it is meter, area will be 1 meter square, and length will be 1 meter. If it is centimeter, area will be 1 centimeter and length will be 1 centimeter square, and length will be 1 centimeter. So we are going to consider that we are having a conductor whose length is equal to 1 and area is equal to 1. So the equation will be modified as rho is equal to r multiplied with length and area 1, so 1 by 1, or we can say that rho is equal to resistance. That is, resistivity will become resistance if area is 1 and the length of the conductor is 1. So we can now define resistivity. Now we got the definition, or we understood what is resistivity. So resistivity is actually the resistance of the conductor. So if you have a conductor having area 1 or unity and length is equal to 1 or unity, then what will happen to resistance? The resistance of this conductor will give the value of the resistivity. So we can define resistivity as resistivity of a material. Resistivity of a material is the resistance of that material of unit length. So that is important. Of unit means 1 length. The value of length is 1. Unit length and unit area of cross section. That is, area is also unity. Unit area of cross section. Okay, once more. Resistivity of a material is the resistance of that material of unit length and unit area of cross section. That is, if you have a wire of unit length and unit area, then the resistance of that wire will be equal to the resistivity. So you could see that the resistance that actually changes with length and area, isn't it? So resistance is depending upon these two factors, length and area. But resistivity, as we can take only unit value for length and area, resistivity don't have any dependence on length and area, because always when you are calculating the resistivity, we have to take 1 meter or 1 centimeter or unit length of wire and unit area of cross section of the wire. So it don't have any dependence, or the resistivity is not having any dependence on the length and area of the wire. So that is the main difference between resistivity and resistance. Resistance depends upon length and area, whereas resistivity does not depend upon length and area. So this resistivity is actually the property of the material itself. That is, if you say that the resistivity of copper is 1.73 into 10 raised to minus 8 ohm meter, I'll give the unit later, ohm meter, then it means that the resistivity is constant for that copper, whether it is 1 meter copper, 2 meter copper, or any length or any area of cross section. It won't change. If it is copper, the resistivity will be 1.73 into 10 raised to minus 8 ohm meter. Suppose we are taking other material, aluminum. Aluminum will be having a different value of resistivity. So resistivity will define the material. If you know the value of resistivity, you can identify the material. Suppose we are saying the resistivity of a material is 20 into 10 raised to 8 minus 8 ohm meter, then we can identify that that material is steel. Okay, so each of the material will be having a value of resistivity. So resistivity will depend upon only the nature. It does not depend upon the length, or it does not depend upon the area of the material. Whatever be the area, whatever be the length, the value of resistivity simply depends upon the material. So the value of resistivity determines a material. If you know the value of resistivity, you can identify which material is that. Okay, so that is about resistivity. Now we'll move to the unit. Once we learn the definition, the second part is to learn the unit of resistivity. Now unit of resistivity can be easily got using the equation rho is equal to resistance R into A by L. That is the equation of resistivity. So here I just put the value of unit of resistance, area and length. So we get unit of resistance is ohm, we have learned. Unit of SI unit of, I'm going to take SI unit, area is meter square, and unit of length is meter, SI unit. So when you put the value, you will get the unit of resistivity rho to be ohm meter square divided by meter. So 1 meter and 1 meter will get cancelled, and finally you will get the SI unit of the resistivity as ohm meter. This is how we find the unit of resistivity. Now let us see the factors affecting resistivity. So as I told, resistivity does not depend upon length, it does not depend upon area. So these factors need not be considered. Now which all factors will change the resistivity of a material? So the first factor anyway will be the nature of material, nature of conductor or material of conductor, nature of material of conductor. That means when the material changes, the resistivity will change. That is, copper will be having one value of resistivity, and iron will be having another value of resistivity, aluminum will be having a different value of resistivity. So the first factor that determine the value of resistivity is nature of the material. And the second factor is temperature, temperature of conductor. So this factor actually affected our resistance also. That is, when temperature increased, what happened? The resistance also increased. Similarly, the case of resistivity, the temperature got a role in determining the value of resistivity also. That is, if the value of temperature increases, the value of resistivity also increases for conductors. Okay, for conductors, mainly for metals. There are certain exceptions in the value. That is, in certain cases the temperature resistivity relation is not linear. That is, when temperature increases, I told that resistivity will increase. This relationship, that is a direct relationship, is mainly for conductors. Okay, suppose we are taking the case of semiconductors. Semiconductors are a category of elements that don't have very good conductivities. So semiconductors, the temperature relationship is just opposite. That is, for semiconductors, when temperature increases, resistivity will decrease. So that is an exceptional case. But for the case of metallic conductors, the relation is when temperature increases, resistivity increases. Since we are mainly doing metallic conductors, we have to keep this in mind, that is when temperature increases, resistivity increases. When you learn electronics and all, you will come across semiconductor devices and all, then this relationship will be important, that is when temperature of semiconductors increases, the resistivity will decrease. So that is the difference between metallic conductors and semiconductors, so keep that in mind. So as told earlier, there is no dependence of resistivity with the length don't have any effect, area don't have any effect, and also the voltage or the potential difference and the current will also will not affect the value of resistivity. That is whatever voltage we apply or whatever current we apply, the resistivity of the material will not change accordingly. So only two factors that will change the resistivity are the temperature of the conductor and the nature of material of the conductor. Now, since we learned resistivity, it is easy to understand the term conductivity. We have learned conductance when we learned resistance. Likewise, conductivity is the reciprocal of resistivity. Conductance was the reciprocal of resistance. Likewise, conductivity is the reciprocal of resistivity. It is represented using Greek letter sigma. So I can write conductivity, it is the reciprocal of resistivity, or in equation form you can write sigma. Sigma is the notation for conductivity. Sigma is equal to 1 upon rho. So this is the relationship between conductivity and resistivity. If you write it in terms of resistance, you can write it in this way. You know the value of rho. Rho is R multiplied with A divided by L. So the L will go up. So the relation will become L upon RA. So this also can be taken as the equation for conductivity. And the unit of conductivity will be the reciprocal unit of resistivity. That is unit of resistivity is ohm meter. So what will be the unit of conductivity? 1 by ohm meter, or you can name that to be ohm raised to minus 1. 1 by ohm is ohm raised to minus 1. 1 by meter is 1 meter raised to minus 1. So the value of, or the unit of conductivity is ohm raised to minus 1, meter raised to minus 1. So that is about resistivity and conductivity. Now one more thing is there. I told you about the temperature relationship, temperature and resistance, and temperature resistivity relationship. Okay, resistance and resistivity relationship. So here main thing to be remembered is, in certain cases there are certain exceptions. So first what I told is, for metallic conductors, three categories I'll mention here. So for metallic conductors, the relation is when temperature increases, the resistance and resistivity, resistance will increase or the resistivity will also increase. Whereas in the case of alloys, that is second category is alloys. Not all alloys, mainly there are certain alloys like constantan, manganine, etc. The resistance relation is, when temperature increases, the resistance and resistivity they will not change much. They will remain almost constant, no much change. Okay, there will be slight change only, there won't be very much change as in the case of metallic conductors. So no much change will be there for this resistance and resistivity when there is a rise in temperature. That is mainly the alloys are constantine and manganine. NiN. Okay, and these alloys are mainly used in constructing the standard resistance, etc. in laboratory. That is wherever we need the laboratory equipments in which the temperature changes should not affect the resistance, standard resistance and all. We use these alloys for that purpose. Now third category is semiconductors. Semiconductors are partial conductors of electricity. Main examples are silicon and germanium. So this silicon and germanium we will see when we learn about electronics. So there you have a detailed learning of silicon and germanium, the properties of these semiconductors. So here when temperature increases, the resistance and the resistivity, they will decrease. So it is having an inverse relation compared to that of the metallic conductors. So these three categories are to be remembered. For metallic conductors, when temperature increases, resistance increases. Then for alloys like constantine and manganine, there is no much change. That is, resistance and resistivity will not change much even though the temperature is changed. Then for semiconductors like silicon and germanium, the temperature is inversely related. That is, when temperature increases, the resistance or resistivity will decrease. So that is all for today.